Josh and everyone. All right, so today we're doing t-test. If you go to comparing two means, you'll see here that we have two data sets that we're going to be looking at. I'm going to just download them. So spider RM is spider repeated measures. And then we have spider BG, which is between groups. You guys have all learned, wrong PowerPoint. You have all learned about t-tests, I'm sure. And you're going to wonder why I'm spending most of the lecture today, but you're going to need to understand the theory behind this because, whoops, that's way too sleepy. Is there a way of, if not, ooh. I thought you could, no. Okay, I thought we could dim those. This will really explain to you all the theory behind basically, how to do an ANOVA, everything. So I'm going in depth because I want you to understand this. Also, some of you may feel like, well, this class, the assignment is not too easy. It's got a point and click. But what I'm wanting you to do is to listen to what I'm talking about today, because it will allow you. I mean, anyone can do. I can teach my son to run a t-test. Okay, on SPSS. I haven't, but I could. No, but he doesn't. A monkey. We could train a monkey to run a t-test in SPSS. But the point here is that someone who understands what they're doing is going to be able to look at these statistics and have some critical thinking about them. So today we're talking about. We're going to do a little bit of review because, and especially since you didn't actually have the review session with Matthew. So how do we build models? We're going to talk about the difference between sample distribution and standard error, what confidence are, error bar charts, and then looking at the difference between and within group designs, which relates to different types of variation. And I'm going to link this to design. So when we look at a stats model, we're assuming that what we're trying to look at actually exists in the real world in a population. This room is becoming a storing place for junk. Like someone's gonna impale their bottom on one of those. So we're trying to explain whatever the phenomena that we're trying to study by collecting data in the real world. And then obviously, we're not actually studying the real world phenomena exist everywhere. We are using the data that we have to try to infer what it is in the real world, in a population. We're making predictions. So we have to look at fit. So we infer things about a phenomena based on these statistical models. And we do inferences. So an inference is a statistical model that is inferring that your data actually represents the real world as closely as possible. But we don't want to, we're assuming it might be close to the real world, but we also have to decide how well does it fit or estimate or infer what is in the population. So fit is simply the degree to which a model represents and accurately represents the data that we collected. So whenever you run an inferential statistic, you look at how does it fit the data, okay? Now, t-tests, we don't really do too much, but for example, when we talk about regression, you're gonna learn you don't just look at if it's significant, you have to look at a whole bunch of other things to see if it actually fits. And then ANOVA, people again just look at if it's significant, but that doesn't mean that it's a good fit. You can have things that are statistically significant that aren't really a good fit to the data. Now, Andy, our friend Andy, he uses this bridge example. It's kind of like a bit abstract, but he's saying, like, pretend that in the real world, we know that this bridge exists, or so the phenomena that we're wanting to look at. We then are collecting data from different samples, I guess you could say, of this bridge. And so here we have A, B, and C. And then we use statistics then to see how accurately do each of these three bridges fit the real world. And you can see, obviously, in A, it's a good fit. That data accurately represents the bridge in the real world. In B, it's a moderate fit. So there's some differences, but there's some similarities. And we would probably look at our confidence intervals for that. And obviously, C looks like it doesn't fit at all. So what we're going to talk about today is how do we know if we actually have a good fitting model? And two ways that we look at. One is to see if your sample represents the real world or the real population, we look at standard error and confidence intervals. Now, I'm assuming that you have looked at these before in some stats class. I remember myself, I'm sure you all, my stats class, we had to like calculate a zillion confidence intervals. I didn't even know what they were, I'll be honest. Like in undergrad, I had no idea I thought I knew what I was doing, but I really didn't. And you'll find that now. Even sometimes now my husband, he has a master's degree in stats. And I'll hear him doing work, and all of a sudden I hear him say, oh. And then I realized it's because he finally, like something that he learned in first year stats, he didn't quite get, really. And his whole 20 years, then finally he's maybe teaching it or trying to explain it to someone. And then he's like, oh, that's why we do it that way. You often have, and you guys will find this with physiology. Do you ever have that with physiology? You're like, you did well in the anatomy, did well in physiology in undergrad. It's now that you're going to be like, oh, that's what they meant, or that's what Jeanette was saying, or Dave. So we look at these two things. So to understand this, we have to also make sure we know about the standard normal distribution. So we've looked at this before. The area under a frequency curve is proposed, it's a relative frequency of observation. So we have normal curve, and we know that, for example, theoretically speaking, 68% of the data should be within one standard deviation of the mean. And this is standardized, obviously. 95% should be within two standard deviations. And finally, we'd have 99.7%. Whoops, pardon me. So here we have the normal distribution is assuming it's looking to a population. So it's assuming a mean of 0, okay? See here? Now, in real life, are we ever going to have a mean of 0? Theoretically, no, that doesn't exist. So what we have to do then to be able to plot our data to the normal distribution is we standardize it. That's what a z-score is. That's what all statistics is looking at, standardizing them so that we can compare it on this normal distribution. So we have to look at a data set and standardize it in order to see how it fits on this normal distribution. We also then standard error. What is it? Well, imagine here we have a population. Notice that you can see here, I'm pointing, it's a mu. So it's saying that the population average, the mu, is 3. Now, they know that because they took a whole bunch of different samples, okay? And if you notice here, they're all from the same population, but they do not all have the same means, okay? One's 5, one's 4, we have a 3, whatever. So we then are plotting all of those different sample means, and when we plot that, we get a lovely sample distribution that looks like this. Remember, that's how they discovered the normal distribution. They had the guy, people looked at tea and hops and beer and all that, and they're pulling all these samples and they plotted them. And can you imagine, like when they developed this, it was just theory, and they were taking thousands and thousands of samples from all these different things in life. And every time they plotted the means, they got this. It's kind of really cool if you think about it, right? It is. It's totally geeky, but it's pretty neat. So no matter what population you're sampling from, it theoretically should be creating, this distribution. And we know that people really get confused between what standard deviation is and standard error. And we know then that when we take a sample from a population, there are many different possible samples. Each sample has its own mean. So sample variation is simply you're plotting sample means to get a sample distribution. To know how well a particular sample represents the population, we then look at standard error. The standard error, is really it's a sampling distribution as well. So a sampling distribution is just the distribution of any sample statistic. Now, we usually do a sample distribution of a mean, but you could do a sample distribution of an F-test, of a T, like you can do it for any statistic, really. But mostly we always look at means because it uses the theory of central limit theorem, is what it's called. So when we have a distribution of a sample, or like a mean sampled under known conditions from a known population, when we have that frequency distribution of sample means, it's called the sampling distribution. So when we look at standard error then, what we're looking at then is if the average of sample means is the same value as the population mean. So notice here, when we plot all the different means here from the different samples, we get a mean of 3, and that is the same as what it is in the population, a mu of 3. Then we know that the accuracy of that average and how likely it is to represent the population. But in real life, are we collecting thousands of samples from our population? No. The only time you might be doing that is like, I don't know, like total basic science Petri dishes, kind of, and that's because it's easier to do. But especially when we deal with humans, you're not going to do that. So how do we know then if our sample mean is accurate? If it is a good estimate of the population mean? Well, we look at standard error. So standard error is the amount of sampling error that we expect. So we're not really collecting all these samples. We approximate to see how is our mean actually fitting with the population mu by looking at the standard error. And you can see standard error simply is calculated by dividing the sample standard deviation by the square root, and you're considering sample size there, that's n. So if you have a large standard error, it's very big, it means you have a lot of variability. There is, that it could be that there's a lot of variability in the means if you had actually collected a whole bunch of samples. If you have a small standard error, it indicates that most of the sample means are probably similar to the population. So you're seeing I'm staring at my notes more because this is kind of theoretical. So we don't actually collect hundreds of samples, we just collect one sample, and we rely then on the standard error to tell us. And we also know, you guys probably learned this in undergrad, we know that as samples get larger, the sampling distribution will more likely have a normal distribution that is actually with a mean that is actually equal to the real population mean. And by the way, that's called central limit theorem. That's what central limit theorem is, that you're assuming that your sample mean can actually represent the population mean. And we also assume that the bigger your sample, the more likely it is to do this. And that's why you might have learned in undergrad a rule of thumb, like you had to have at least 30 people in a group to do a proper T-test. Did you ever learn that? Like there was this magical 30 rule. Why? Because we know that at least at 30 units, a sample size of 30 or greater is most likely to represent the normal distribution.
Was there different tests? Like if you had, was it like, remember doing 2 tests, one for lower population, one for larger population?
Yeah, there's a correction you can do, and I can't remember what that was, but you also often do a non-parametric test if you have too small. But you're right. I think I'm going to say I haven't done this because I don't actually go and done this by hand in a long time, but it had to do with what critical value you look at on the T table too. Okay. And it was like, there was one table for if it was 30 or over, your sample was 30 or over, and there was another table if it's 30 or less. And all that is it makes it more conservative. So you have to be even more confident. You have to have a higher T-test value to say that it's significant. So it's to be like more conservative. And do I have? Sorry, guys. I'm just, pardon me. I had this picture, and I'm just making sure that I. Oh. Sorry, I'm just going to. I had made some changes to my file, I thought. Well, I have a picture of it then. I'm just going to draw. So, and then also has to do with the spread. So if you have, if we look at this distribution, we're going to have a smaller standard error because the variability around the mean is smaller compared to a big thing like this. We have greater variability. Therefore, in this case, this sample is less likely to be representative of the population. Okay? No, sorry, this looks kind of peaked. I didn't mean to draw, I'm just about normal. Pretend this is a real bell curve shape, okay? So this looks left over. But we can be more confident that this is the true, that represents, this sample mean represents the true population mean compared to this one that's going to have a greater standard error. So when you look at standard error, when you're comparing things, you want to look at your standard error. If your standard error is really, really big, it means you've got problems in your data. It might be your data was not collected reliably. You might have measurement error. There's all these reasons. So looking at the standard error, as an example, you'll notice in my class, I'm making a report, mean, standard deviation, and standard error. If you note, most of your colleagues probably don't ever write the word standard error, okay? But the standard error is more important to the reader than the standard deviation because the standard error tells the reader how accurate that mean is. So if I saw in the same data set, I've seen this, you might get a standard error of, 3.15. I've had, over here, you could have 12.31. Woo, woo, woo. The emergency statistical ambulance has to come. Because that's telling me, and if these were, let's say this was 2 groups, and I was looking at, control group and treatment group. Well, something went really wrong in my treatment group there. That you shouldn't have standard errors. So standard errors are important to look at. For example, you guys want to look at the standard error you have for each condition, for each, treatment that you're doing. You want to look at all of these things. They tell you something about what's going on. Another example was, I know Feb. We were doing like Mohammed Ismail did, like the validity of the different metabolic carts, okay? And so he collected some of his data, and Fabien sits down with his students and quickly looks at it all immediately, like to check everything. He saw like a massive standard error issue. in one of them that tells them something. What happened? Well, the student forgot to calibrate the thing. I don't know what I'm talking about, okay? But he forgot to calibrate the instrument. So they had to redo that whole condition, like recollect all the data for that one thing. Now, that's kind of a pain, but that's better than realizing that when you are about to hand in your thesis, right? So these numbers tell you things.
You guys seen that paper?
It's a good paper. Why?
Maybe that was his go-to paper for us for that course. We knew his thesis in it.
Oh, Muhammad Ismail's?
Yeah.
Oh.
That was the go-to paper for us to know. So like that was the Bible.
Okay. Oh, because it talked about metabolism.
It was the carts, right? You need to know all about the carts. So the different.
I know more about the carts now. Anyway, yeah, we just submitted that paper actually. And my husband's on it too, because he did this one cool thing about it. Anyway, all right. So besides looking at standard error, the other way we can tell how well does our mean actually fit or represent or infer the population mean? We can also look at confidence intervals. So what is a confidence interval? Since the population mean is never going to be exactly equal to the sample mean, that doesn't happen in real life. I mean, and how could you possibly really know? Remember, all of this is kind of theoretical stuff. Like, we don't really know what a population is, right? It's mu, it's theoretical. The only time you're ever going to know what a real population mean is if you actually collected data on every single person in your population, which I guess you could if your population was like a village or something, I don't know. I mean, you could. I mean, that's what the census tried to do, right? Mary and Joseph, everyone had to go there and get tallied up. Now we can't do that. They don't actually, so they used to actually physically count every single person in a city. Now, and then knock on the door. They can't do that now because we have population issues. So now what's a census? It's using estimates of how do you collect people in a whole country to infer then what the population is. So we don't really know. So we have to look at a confidence interval. So around the likelihood that it will actually cover the population mean. And so we can quantify our level of confidence that the population mean is actually covered. So different samples will provide different values of the mean. And as we just discussed, we could use the standard error to look at that. But a different approach is to assess the accuracy that the sample mean is to calculate the boundaries in which we believe that that sample mean is actually representative of the population. So a confidence interval provides a range of values. It's based on an observation of one sample. It gives information about the closeness of an unknown population parameter. So this isn't just for means. You can give it a F-test and report the confidence interval. There's all these different ways, okay? This is important for you to know because confidence intervals sort of go against hypothesis testing, okay, because it's not about p-values. So how confident are you that the mean is there? Confidence intervals are becoming more and more popular. They're becoming more meaningful to people. Now, what I've been recommending is that like I've helped people submit papers and they do put confidence intervals, and especially if the journal isn't up to date with statistical stuff, like especially the XPhys ones, they will say, you can't just, we need a p-value. Like they're so into if it's significant or not, and they actually care if it's like 0.501 versus 0.504, like it's ridiculous. Like that doesn't mean anything. The difference between that is ridiculous. Like that's like 1 in a Are you more confident in 1 in 1,000 or 3 in 1,000? Like, it's stupid, you know, so little of a difference. So what I recommend and what you're going to do in this class is you report confidence intervals, effect sizes, and p-values. That way you know how to do all of them, okay? Now, it's all stated in terms of probability. So this is from from the textbook. If you notice, if you haven't figured this out from reading it, Andy Field collects funny research articles that he finds, okay? Like weird things that people have done, and he thinks they're hilarious. And then he like uses them as an example. That's why it's all sex, drugs, and rock and roll examples. Some of them he made up. No, but he actually like finds.
So like the Viagra studies are real one.
Yeah, like he finds these funny things and then he thinks it's funny. So he comes, and then he like manipulates. Then he doesn't actually use their data. He just uses like their design and what the variables are. So here, I don't know why, but there's a Japanese quail and they wanted to know its sperm count. Okay. So what happened here? So they took from 50 different quails. They gave the quail a magazine and had him go in the bathroom and got the sperm count. And they then plotted this, and we know, if you look at this, this awful, like horizontal, vertical. I had to like do that in my head for a second. Left, right, Angela. Do you guys know this one? Some people, when I was a kid, L for left is your finger. So I was like a kid in, doing plays up at the top, like 8 or 9, and be like, and then I had to exit stage right. Oh, you see me on the stage. Anyway, vertical. So the vertical is the population statistic, meaning that in the population, the average, the mu is 15 million sperms per, I don't know what, per gram. I'm not sure how that is. The interval, which is this, the length of these whiskers, okay, that is the estimated range of which the value is likely to include this unknown or this population mean that we're trying to figure out. And the percentage is how confident you are. I'll explain this in a moment, but we just usually use 95% confidence intervals. We could make them 80%. We could make them 99. That's arbitrary, okay? So if you look here, they even have it. Notice that some of these whiskers, these intervals, touch the vertical line. Some of them include. So for example, here, look at this bottom one. That's the mean that the sample, notice it's so close to the population. This one's pretty accurate then, okay? Whereas we have 3 of them that do not contain the true mean. So when we look at a confidence interval, it will tell us, does it contain the true mean? And it will also tell us how accurate do we think we are? And I'll explain this. The wider the whisker, the less like you have then greater, like there's more variability that you could get. Compared to a shorter interval, you can be more confident in that. And I'm going to give an example in a moment. These are, a confidence level then is 1 minus alpha. So alpha is simply how confident we want to be. Usually we say 0.95. So 1 minus 0.95. Or sorry, alpha would be 0.5, pardon me. 1 minus alpha, so 0.95. So we have the sample statistic, confidence, we call that the lower bound of the confidence interval, and then we have the upper bound of the confidence interval. And these limits are constructed such that a certain percentage of the time, either like 95% or 99%, or you could say 80, the true value of the population mean will fall within these limits. So a confidence interval then gives you an estimated range of these values that is likely to include this population parameter. So it's an estimated range. If we have different samples and we've taken them repeatedly from the same population, like quill sperm samples, the confidence interval is calculated for each sample, and a certain confidence level then will be known for that population parameter, theoretically. Okay. So confidence intervals, I said they're usually 95, but you could do 90, 99, 99.9. You can make whatever number you want to. Okay? Why do people pick 95? Because a zillion years ago, when the guy developed the studentized T-test, that's the number he picked. He said he wanted to know if there was going to be 5 bad hops in the barrel. Okay? And that's it. We have just used that forever and ever. And it really doesn't make any sense. Again, how confident do you want to be that didn't happen by chance? If you're taking a drug, what do you want them to be using? 99.9 FM. That's what it said. We can be 95. Now, let's say we're doing a stretching protocol for athletes, and they're not even elite athletes. Do we need to be 95% confident? I don't think so. Like if it's an applied thing, like who cares? Why not you be 90% or 85? You know? Like I think it depends on the implications of being wrong. Obviously, when if there's any risk of dying, you want to be 99.9. But as an example, like, and you can argue this, by the way, often it won't get published, so that's why people do it this way, okay? But like an after-school program for children that I want to know if they socialize well or something. I don't need to be 95% confident. Why can't I be 80 or 85? Okay, you will see people starting to do this more in journal articles. However, they always have this great big blabby blab about it. And if you don't, and you have to do that because if you don't explain why you use that certain alpha level, the reader thinks that you're just fudging your data to find something. But if you say that you should be deciding how confident you want to be a priori. You know what that Latin word means? You should do this all the time. A priori means before. So, is it still on your computer? Okay. Sorry, that's my worst fear of my life. When I was in my master's, I lived in an apartment, and the fire alarm went off at weird times sometimes. And there was a PhD student that lived on the floor above me. It was mostly older adults that lived in the apartment. And 3 in the morning, the alarm goes off. All the older adults have their cats. And her and I have backpacks and books and our laptop, This is what I had to save. So yeah, if you a priori means that you're allowed to make a decision that you don't want to be this confident, but you have to tell the reader, I made this decision before I collected the data. Okay? That means you're not fishing. You made a reason. You're telling, even in ethics, you'd say, I'm using an alpha of, I'm going to be 80% confident. The width of the interval is important. It tells us something. It tells us how uncertain we are, or certain. A very wide interval may indicate that we should collect more data. You're hoping that your interval is narrow, is small, because it means that it probably is a good estimate. And I'll just use this example. So if I said to you, so you have to listen, well, I could, let's see, I'm going to be, okay. I'm using a great example. So I could say to you that at the beginning of this class, I am 95% confident that your interval, like confidence interval in this class, 95% confident that you will get an A in this class, but the confidence interval ranges between 80 and 85, meaning that you could get an A, but I'm not totally confident because you could also get my interval so wide that you could get a 55 all the way up to an 85. Okay, so that's a very wide interval. Or I could say to you, you could choose to be 95% confident that you would get a B, and the interval was between 70 and 80. This is a gamble. Think of it as gambling. Which one would you place your bets on? Are you going to gamble for the A, but you have still a very good chance of getting a 55? Or are you going to put your money down on, okay, I'm going to pick a B and I know I'm going to get a B then. I'm telling you that you're going to have a B, 70 to 80. Which one would you choose? No, just forget about the gambling part. But to be confident, we would probably pick B. You're going to be more, it has a smaller interval, so you know for sure that you're probably going to get that grade and it's going to fall within that range. The other one has a much wider interval, therefore, it might be a higher grade, but let's do a different thing. What if this was sprint times? And I said, if you do stretching method A, this doesn't tell you. I'll just change the numbers. Sprinting method A. I'm 95% confident that your sprint time will decrease between 0.5 seconds and 5 seconds. Big wide. Or if you do B, I'm 95% confident that your sprint time will be reduced between 2 and 3 seconds. It's a smaller one. But if you were going to try to do something to reduce your sprint time, even though the B method isn't going to give, you potentially are going to have as much reduction in sprint time in seconds, but you're more confident that one's going to work. It depends on if you're a betting person.
So if you put that in the literature, would you still show a p-value or?
No, theoretically speaking, you shouldn't put p-values with confidence intervals because p-values are around the hypothesis testing. Confidence intervals are another form, okay? But research is more and more moving away from p-values and moving to confidence. So I would say we're in like a transitional time in research. So you'll see, in XFIS, I noticed that they're more and more now reporting p-values and the confidence interval, like both, and that's to suit either reader. But theoretically speaking, it's like putting, it's like writing in French and in English, or like writing theories that are totally, I don't know, being a Catholic and that's not the best, but that's not extreme enough, but like paradigm shifts, okay? Being the Flat Earth Society and the Round Earth Society, okay? It's more like that. That's the thing. I don't know if it's true. Everyone said my grade 7 science teacher was president of the Flat Earth Society of our local chapter, but I'm not sure. That was the legend.
A lot of times people will now in our design reading, they'll report the confidence intervals and the means in table, but then they'll bold the ones that have a p-value of 0.05.
That's common. Yeah. So, and by the way, you don't have to bold. You can tell from the confidence interval is statistically significant because, and I'll show you that in a moment, but if the confidence, I'm not going to show you in a moment. I'm going to show you right now. You just have to look at the, so confidence interval, okay, so remember that In that normal distribution, sample distribution, it's assuming a mean of 0. Okay? So with confidence intervals, if the interval passes 0, so you've got a negative value and a positive value, it means that it's crossing over the mean, and therefore it's statistically significant. You don't actually have to look at a p. You can just look at the confidence interval. If the interval goes over 0, meaning it's got at least one positive and one negative, then it's statistically significant at the 0.05 level. Okay? So that's why people do both. But for example, it doesn't make sense to me. You shouldn't be reporting a 95% confidence interval and then reporting that the p is 0.001 because this is for 95. In this case, you would change this one to be 99. You'd make a 99% confidence. That's the thing that kind of is like by talk. I don't know. Is that you don't want to be giving a confidence interval in one type of confidence, and then you're giving a different kind of confidence from the p-value. But why do they do that? Because the people don't understand if it was a 99.9 confidence interval. So statistics is there's correct, there is what's going to get published, and there is trying to meet the needs of everyone. Like, that everyone can understand it. So I think it's best to kind of put quite a few different things. I'm not going to make you calculate confidence intervals. It does, but you can though. It's easy. You don't always get confidence intervals for everything in SPSS, and you can calculate it. So you might have done this. You take once you have the standard error and the mean are known, you take the lower bound of the confidence interval, and it simply equals your mean minus 1.96 times your standard error and the upper bound. And so you get your upper and your lower. If your sample mean is always in the center of the confidence, it's always in the center. So if your confidence interval is small, then the sample mean is probably very close to the true mean. If you have a very wide confidence interval, again, it is saying it could be different. So we want to look at our standard errors, because the smaller the standard error, the more confident we are that our mean is good. Then we look at confidence intervals, same thing. It's now telling us, it's a little slightly different, but it's saying the likelihood that that our sample mean is actually representative. So you want it to be small. So in some of my research, like I might have I have pretty large confidence intervals because you're dealing with subjective things. Okay. So, but again, that can tell me there's a problem. So you want to always, I guess what I'm saying to you too is it's a good idea to quickly run some exploratory statistics when you're collecting data. Have a little look, because again, there's no magic statistics for collecting shitty data. So that's why you do pilot tests. That's why you do a quick little exploring. You want to know if something's going wrong in your data at subject 4, not subject 25, right? So it's important. A lot of people don't play with their data until they've collected it all. But you want to be looking at this stuff because you might be able to catch errors. So error bar charts. Error bar charts, you guys probably don't know this, but you see them all the time. If we went downstairs and walked around at all those posters that all look exactly the same, by the way, which I find boring, but that's how they like it. I'm like, I can't even tell the difference between them. But they all have error bar charts, but they just don't call them that. They don't know what it is. So it's a graphical representation of the variability. It indicates the error or uncertainty of that measure, of that variable. Gives an idea of how accurate your measurement is or how far you are from your bridge actually representing the true bridge in the world. And it's usually looked at as standard deviation. So it's usually one standard error and a specified confidence interval. So you guys have seen these. this is basically what in exercise physiology, a lot of data is only presented this way, okay? But it tells us a lot of information. We can visually compare the means. We can determine if they're statistically significant. And I can also see how good a fit it is to the model. For example, you'll see there's a small variation. These ones have larger. You can see the intervals on these. So I'm going to be honest, when I first started working here, I've never did error bar charts. It's for visual, okay? I thought they were silly. And they didn't tell you very much information. But I've changed my ways. They actually give you a lot of information, and a good benefit too is that everyone in the world can kind of understand that, okay? So it doesn't matter, this is, visual descriptions provide more information. You don't have to totally understand statistics even to get that, right? We can see right away that, for example, I don't know, pretend these were different experiments. Right away, we could see that, well, this one, the control group is way different than the other groups. Then we have, I've already talked about this, but you just have to understand this again, just in order to get what I'm speaking about next, between and within subjects' designs. So we have X is your experimental treatment, O is observation, R means random assignment. Again, I'm going to emphasize this again. Is random assignment the same as random sampling? No. Random sampling is how we get the sample. Random assignment is after you have your people, if you're doing an experiment, how do you assign them to groups? We could have a purposeful, convenient sampling technique by going out right now and grabbing every person you see and asking them to be in our study, okay? There's sample error there, though, okay? Doesn't mean it's a good sample. Then you randomly assign those people hoping that they're going to be equal groups. Are they going to be equal? No bloody way, because it wasn't real random assignment, okay? So the ideal is random sampling and random assignment. That's also why you have eligibility criteria. When you aren't random sampling, for example, a typical XFIS is a male undergrad or graduate student between the ages of 20 and 25. Well, less variability. They have athletic capabilities, or at least recreational strength training or whatever. Again, that's to help reduce the variability. But it's not going to be by chance. It's in your eligibility criteria that you are trying to reduce that. So we have two different types of designs. We can do between groups, or what's called between subjects, or it's called independent design. You need to know this or you're not going to understand things when you read things, okay? These are all the different words. It depends on the discipline. And I don't know, I would say, most people say between, I use the word between subjects myself. Repeated measures design is really called within subjects. It actually is kind of not accurate to call it repeated measures designs, okay? Because there's many types of repeated measures that could be just time series, but that doesn't mean that it's an experiment. I can collect data over time every year the rest of my life, but I didn't actually manipulate anything, okay? Longitudinal. So what's the difference here? Why do we have to care about this? So here's my first example. We have a independent design between groups. I've randomly assigned them to two different experimental conditions. So group one is drinking coffee, a drink of the gods, and group two is tea, which is also a good drink. only if you can't find coffee, in my opinion. And we took blood pressure. So I don't know. I mean, this is kind of like, well, I think of this as a grade 7 science experiment. Okay. So, but I'm picking something so that you get it, understand it. So in this case, we have, they're independent, they're not the same people, and they're totally different conditions or that they're doing. In contrast, we could do within subject design or repeated measures. So I use repeated measures term as well, only in order to communicate to this building, they use the term. In this case, no random assignment, one group. We say, first you drink the coffee, then I take your blood pressure. Maybe the next day they drink tea, then we take the blood pressure to see which one is going to have the largest effect on blood pressure. Now, to understand this more, we need to think about types of variation. So I told you that this was review from undergrad. You probably never learned about this part though, okay? And it makes sense, like, it's cool when you think about it. This all links statistics to design. So unsystematic variation is variation resulting from random factors that exist between groups. So in this case, here we've got the same people doing the same conditions, okay? They come in, day 1, have coffee, blood pressure. Come in day 2, have the same coffee, blood pressure, okay? We would expect that certain factors that are external, like age, for example, age isn't going to change, right? You're 1 day older. Doesn't change anything. It's not going to, what else? We would, because it's a short interval between collection times, even if this was a week, physical conditions not going to really change between collection times. It's going to be pretty much the same. So people's age isn't going to change from one to the other. But if we actually did this, would we get the same mean for each time? No. This mean, even though they're the same people, the same everything, this mean is never going to be the same as this mean. Why? Because the outcome, the blood pressure, won't be identical because there's going to be small error. There's going to be some kind of differences. And this variation that is due to unknown things that we can't control, like it could just be like, the very millimeter placement of the blood pressure cuff, or, or I don't know, like anything, right? It's just error. It's never going to be the same. That error is called unsystematic error, okay? The stuff that you cannot control for, regardless of perfect eligibility criteria, perfect random sampling technique. You could do everything best practice, gold standard. You will never have the same data for the exact same condition, and that is just called unsystematic error. We can't do anything about it. Now here we have, I'm showing you systematic variation. So systematic variation is variation due to the manipulation of one condition. So in this case, we're manipulating something. Now we have coffee and tea. If we introduce a manipulation to our independent variable or outcome, sorry, the blood pressure, or the independent variable is condition, sorry. Condition 1 is coffee, condition 2 is tea. Any difference now between the blood pressure between these two conditions is probably due to our experimental manipulation. So if we're comparing these values, the differences we can say is due to the manipulation we did. The difference is if we found, I'm making this up, but theoretically, I believe, coffee will have a greater effect on blood pressure than tea, I think just due to caffeine. Yeah, and that all depends. And by the way, you might not need to this, but when I was pregnant, you might know I drink a lot of coffee. Okay. Or maybe I had a little too much this morning. So you're not supposed to have it when you're pregnant. They talk about this. So, well, of course, I'm going to find a reason why I might be able to have a little bit, right? So I did all this research about it. And what are the values? Look at the confidence intervals of the studies, right? Got to care about that. And then I learned about how different beans have different, and your roasting method. Dark. If you're tired, don't have dark roast. You have light roast. Light roast has more caffeine. And then the brewing. So a percolator coffee. Do you guys know? My parents-in-law have one. I don't like the taste of it, but the one that you put on the stove and it bubbles up. Okay. And then that's the least. Then the drip. But I had French press, like Bodum. That's the most. So then.
Because I found French press tastes the least strong for some reason.
Is it? Well, it's sitting in there.
I don't know.
The worst is in Costa Rica, in Central America, they put it's unfiltered and they pour it in this thing and it drips. And I didn't realize that, but I had one. Yeah, it's like this weird, it's just a cloth bag. And they do it right at the table, too, with your cup. And the cups were small, not like our, big Tim Hortons one. And so I had a little bit, and then I asked for another coffee, and I probably had 3 of these coffees one morning. Holy smokes, I ended up with like an anxiety attack and chest pains because the caffeine was so much higher. And then I was like, okay, well, yeah, people aren't, only North Americans, we drink coffee that's not as strong and we consume more of it.
What about espresso?
It's actually less caffeine. Yes. It's just that it's stronger. So anyway, so when you're pregnant, you can have a little bit of caffeine. You just switch to the drip and you have dark roast and you could have, I figured I could have one medium Tim Hortons, a day. And I would split it in 2 and put hot water. So there you go. Okay. Now, when we look at unsystematic, in this case, this is different. Now we've got 2 groups, and they're doing the same condition. Are we going to find the same results between these groups? So different people in different groups, but it's the same manipulation. I gave them both coffee.
Theoretically, you'd want to, but you're not.
Right. You're not. Because we have variation. We have, the groups contain different people that are going to have vary in age, resting heart rate, all that sort of stuff. So when you have 2 groups, there is more unsystematic variation. Because you can't possibly, even if you randomly sample, even if you randomly assign, you will never ever be able to make them exactly the same. And that is why repeated measures is awesome, is cool, because it helps reduce unsystematic variation. In this case, we now have 2 different conditions, tea and coffee. We will still have unsystematic variation because we have different people in different groups. We are going to have systematic variation because we have 2 different conditions, tea and coffee. So both types are going to be present. So what we really are doing in statistics is we're determining in your experiment how much variation in the outcome variable is due to unsystematic variation and how much is due to systematic variation, and we're comparing that ratio, and that's how you figure out what a t-test size is, or the F. It's all looking at systematic versus unsystematic, or what you found because of your manipulations versus error that you, in your experiment, that you cannot control for. Just error. So repeated measures, again, I want to connect to design. So repeated measures design, we have, if we see differences in conditions, like hopping on the left foot versus hopping on the right foot, or between coffee and tea, any difference then is it's a manipulation that was carried out on the participants. So it's going to be caused by that manipulation of the independent variable, and any other factor that might affect the outcome from one time to another. That could be that you didn't collect the data at the exact same time of day. It could be that you were up late and you couldn't read you didn't read the thermometer or thermometer, whatever. The cuff. You couldn't read the blood pressure cuff very well, okay? You forgot your glasses, right? And you couldn't read. There's all these things that could be errors for what happened. Whereas in independent design, if there's differences, it's because of our manipulation, our experiment, but it also could be that there's differences in the people. There could be such differences in the groups. And that's why it's important to randomly assign in independent design. That's why we randomly assign, because we're trying to remove unsystematic error between the groups. So, random assignment, why do we do it? It reduces unsystematic variation. It tells us if we to see whether the experiment has an effect, and it also reduces confounding variables. So it is important. Now, you don't have to care about this for usually for repeated measures, but I notice now more and more in the labs downstairs, people are now more and more using two-group design. So they're doing a mixed model, meaning you've got two groups, like the biofreeze study. There was a shod biofreeze and the real biofreeze, two groups. They also did repeated measures. So that's called a mixed design, because you have a within subject factor and a between subject factor. And that's a cool study as well. Then we have randomization. Oh, sorry, another way of randomizing. So it's called counterbalancing. So you guys probably read, you have studies where, especially when they're worried about a testing effect or an order effect, in order to remove these things, they call it counterbalancing. Counterbalancing is changing the order in which a person participates in the condition. So, for example, in this case, I would randomly choose who's going to drink coffee first and then the tea. Some of the people would be doing the tea and then the coffee. Okay? This is called counterbalance design. Fabian students, or in every single thesis presentation I've been to, the student will say, I'm doing repeated measures design, and I'm randomly, I'm randomizing the order of the conditions, okay? And Fabien will put his hand. You are not doing that type of design. You are doing a counterbalanced repeated measures design. This is how so just so you know, if you do this, you should use the word, a counterbalanced repeated measures. I don't know why Fabien, he's trying to show that you're accurate. But see, you don't actually have to say, I randomly did the conditions. If you just use the word, a counterbalanced repeated measures design, you just told the reader that you did that. You don't have to use so many words. Again, I'm stressing, it makes me really mad that scientists and researchers are lazy about describing their methods and their statistics. If you use an accurate term, it might take up one extra word in your whole paper. You don't have to be lazy. So we would use this counterbalancing to reduce practice effects and boredom effects, and could be learning effects as well. So how does this all link to what we're learning today? Well, there's two types of t-tests. We have independent and dependent. Independent t-test is also called the studentized t-test, is also called the independent samples t-test, so lots of names. Whereas dependent t-test, or more commonly called a paired t-test, okay? So you have to know these words, they're all the same word. Paired t-test and dependent is the same. So if we have two groups that are independent from each other, we must use an independent t-test. If we have repeated measures design, we use a dependent. So the rationale then for a t-test is we expect means from two samples to have the same mean if they come from the same population. So our null hypothesis, or H0, is that we assume that the manipulation of the treatment of the independent variable will have no effect on our outcome, or dependent variable. That's what statistics is testing. It's assuming there will be no differences either between the groups or between conditions. So we have to compare then the differences between our sample means that's collected and what we would expect by chance. So you compare what you did see to what you expected to see if your null hypothesis is true. So again, if the standard error between sample means is small, we expect those samples to have similar means. If our standard error is large, we would expect that this difference might be by chance alone. Another way of saying it, the differences, and if your difference between samples is large, again, that might be, it could be by chance. We could assume then that the sample means in our population fluctuate a lot and that we collected two samples that really differ from each other. Or we have to assume that there's really no difference. So in this class, I'm going to emphasize this many times. Every single statistic you learn in this class, inferential statistics, which is using central limit theorem, is this. It's looking at what is explained by your statistical model divided by what is not explained. Another way of saying that, it is the systematic error, the effect, over unsystematic error, the error in your model, which could be measurement or just cut because. And every single stat is really looking at that. Another way of looking at this is, I know Jeanette talks about this I know you guys had Diane, so maybe she doesn't, but I know in tech, when Jeanette's talking about EMG stuff, I hear her talking, there's the signal and there's the noise. She talks about that. So it's the same thing. It's just looking at EMG data. You're looking at how much systematic error, and the noise is your unsystematic error. So when we look at this, we see that what a t-statistic is doing. So in this class, I'm not making you do calculations. And you might think, why? Because being able to divide stuff by a bunch of numbers and put it in a calculator does not mean you understand it. It means that you were able to memorize the formula, okay? I want you to think about this stuff theoretically. When you go into your next stats class, or you go learn on your own, having statistical fun on a Sunday, you then can figure out the formulas and you'll understand things better, okay? But my pedagogy of teaching statistics is that I think that when you're being an applied researcher, too many researchers don't actually think about these things. So, and that's because they learned about formulas. I want you to be a critical thinker about what is going into your data and how can you actually not just look at the t-test, but look at what does this mean? What do these values mean? So in this case, we've got, here we have two independent samples, so two groups, okay? And what we're doing then is the top part of the equation is the difference in group means. The bottom part of the equation is looking at the variability of group 1. And how is that different from the variability of group 2? And again, signal versus noise. If we had great big wide confidence, like variability in one and not the other, like they're not going to overlap. So you want your error to be small so that it is more likely then that it happened by chance. Oh, not chance, pardon me. So when we look at error bar charts, the overlapping confidence interval tells us something. So these are, I guess this is the quail stuff again, sperm count. So these are two different quails. And because they're, notice that the lines are parallel to each other, okay? So because they're saying the same thing, it probably means that our experiment didn't work. They're coming from the same population. If this was coffee and that was tea, it's saying that coffee and tea had no difference in blood pressure. If, however, we see different error bar charts plotted on the same graph, pardon me, there's no overlap. So it tells us that our samples are from two different populations. Therefore, it's telling us that our experimental manipulation likely did have an effect and that there are significant differences between the groups. Again, while I never liked error bar charts before, I'm showing you that just plotting this, we don't even have to run a t-test. We can just plot these means, put the confidence intervals, and we can see visually with our eyes that these are from different populations, so they're different from each other. We'll take a break, okay? The rest of it. I know that's very theoretical. Very soon we'll do that. Did you make this?
No. I made a couple of them.
Oh, I was going to say, you did a great job today.
I know.
I made one for my sister, and I didn't have one of these things. And I went to a student and asked if I could please throw it and measure it. Figure it out.
Never went to the local Sonic or the local knitting club.
I've been to quite a few stitch and bitches.
Oh, yeah.
Yeah.
Stitch and what?
They call them stitch and bitch.
Oh, so you go the bitching part is a part of the process of it.
No, it's mostly that people are stitching. They're just talking and bitching.
Yeah, no, I understand. Growing up with crazy grandmothers and stuff.
Stitch and shacks.
I agree.
It's scary. It's monotony of people knitting. Like they can have a full conversation through math. They're completely doing it.
I can I'm not a crocheter.
Oh, okay.
And
That looks so different. It's like the little tiny stitches.
oh, I don't do that, but yeah. And guess what? We're good. Crochet. We should know this is new blenders. And then fishing. That's like a new
Okay. It's the same pattern. Just very pattern.
Oh, right.
So probably the nice, well, I mean, I guess way back.
Yeah. I don't know, like men, like back home, they would always do their knits, like grandfather. Now, this is how they were done, but see, growing up, like I think way back when you started, the women's job was always anything at home that required to be done was done by the women. So children was one, probably feeding the dog, all the transportation, keeping the fire, and bringing wood and bringing water, like cooking, and then creating clothes, making clothes and stuff.
Yeah. My great grandmother, my grandfather was a Scottish shepherd. He was born on a dozen big farm in Minnesota. Okay. In Sod House.
Yeah.
And his father, so everything was, I picture, it has some like, like pictures and stuff like that, you know? Like a photographer must have done. Anyway, and it took him, so he would start whenever he could in the morning, plow, he would do one line, have lunch, and the next line back.
That was amazing.
And so this is how, and then of course they did everything by community, so when it was harvest time, we hired local people, you know? So they would be like, my grandmother said there could have been 30, 50 hired help from that. At a certain point. So anyway, and you can say like everyone laughs about how it must be hard on his dad. It's like his mother.
Yeah.
So looking after the 7 kids,
Yeah.
the house, feeding 50 farmers, breakfast, lunch, and then washing all their clothes. But there was no women help.
No, it's crazy. I know it wasn't to that extreme like back home, but a lot of times like the more successful fishing. No, they have the what they call like or people like crews, right? So they have several crews of fishermen. Like,
Oh, yeah.
Put them up in their own bunkhouses.
Yeah.
Or in the house. And the wife.
It's too early.
That's the way it was.
Well, the children, my grandfather remembers, and he remembers many times.
Yeah, no, he was the 28
He was up in
5.
the rocking chair
This is the guy.
with the baby in a bottle.
Like someone got
And tying with stars. So he couldn't drop the baby or get out of the rocking chair and fly out. Well, that was a job, but he had to be tied in because he was going to living with sibling.
I didn't look at their names.
And then this is really good. Of course, people died. They were the only ones who had silo, or greenery in it. So all the community all around, their dead bodies were stored in there. So he said, like one year, I remember, one guy used to go into town and he'd go to the bar. He got drunk and he came home. His horses arrived at his farm and he was dead underneath and dragged. So the horses brought him home. That Mr. So-and-so was in there. And then someone else had a baby die. And so he said when he was 5 years old, playing in the greenery, and they'd do like, once he was drowned in that, anyway, and then he just had to be careful not to touch the baby and Mr. So-and-so's bodies.
My father was 9, and his 13-year-old sister looked after him for a full summer. Like those.
Yeah.
One of the Fairport community, so like there was a summer home and winter home, so they stayed in the summer home while the other kids stayed in the winter home, but I was in the summer home.
Did you pick your dad?
Yeah, my dad, so he was 9, his sister was 13 or something, she looked after him full summer.
Oh, like nobody around it?
No, because the parents had to stay in the day to like work, and she had to stay there to look after the old home and the other communities.
And this is your dad?
Yeah, this is my dad, so this was only back when I was 70.
It was before, child life.
Like he had a whole bunch of family out there that was all around him, but like in the house together was just his sister. It's for
All right. Everyone's back and ready? Ish. All right. So I have this, you'll see our spider data.
Which one?
What? It didn't open. Oh, wait, it's because I downloaded it. Okay, sorry. Oh, my brain's not very smart. Okay, we are, which one? Good question. Let me look what I'm talking about already. We're doing spider repeated measures. So spider RM. Okay, very simple here. I'm making a silly example up. Oh, I don't know if this one follows, if I took this from the textbook, I can't remember. But here we have, what this data is we've got, we're measuring anxiety on some type of score ranging from 1 to 60. Higher scores indicating greater anxiety. And we're trying to see if we have two conditions, someone holding a real spider in their hand or seeing a picture of a spider. And we're measuring, which one's going to cause more anxiety. Okay, this is repeated measures. And so obviously the person is doing both conditions. So I'm going to be going back and forth between the PowerPoint and the data. We're not going to be following a lot on the interpreting the output, okay? So just like in your assignment, it's the same thing. Now, in this case, I'm showing you dependent versus independent t-test, and it's the exact same data. It's just one's repeated and one is not, and you'll see the cool thing that happens. In your assignment, you will see that there is, like, they're different, like they're totally different studies, okay? But you have an independent data set and a dependent. So the first thing we want to do is explore our data, okay? So we would, just like you did for your last assignment, you're going to go into explore. We're going to put both our variables in here. I'm going to get make sure I have I forgot, I want outliers. And we might want a histogram instead of a stem and leaf. And that's it. And I forgot to click on normality plots. And we would here then see, you can see on your assignment here, on the output, I need to say some stuff about this. Here's our histogram. Obviously, it doesn't look very normally distributed. It's kind of weird data. I would want to report, again, what my mean is, what my standard error is, what my standard deviation is. I also want to look at normality. I'm going to look at my skewness and kurtosis scores, divide the skewness by its standard error to standardize it, kurtosis as well. Same thing as for this assignment. I then am going to say something on the second page. You'll see the box plots. I then will say something about these if there's outliers. And you can see that there's no outliers at all. So I would mention that in my pretty plot. And I want to show you the difference here. Look at this one, perfectly symmetrical, right? We can fold that in half. So it looks pretty normally distributed. In contrast, here's our real spider. It's not perfectly symmetrical at all, okay? And so you can see that, if we looked at this on the top, it means that there's a great big tail after the mean. So you can see that in the histogram. Okay, there's a big, the mean is over there. There's a gap even on scores. And I would also then look at my normality. And you guys can't see, so page 3, you will see that test for normality. It says 0.200. Okay? Is that significant? No, it means it's not statistically significant, right? Now, you don't, in this case, you know how I tell you to always put a p-value? Okay? Don't put, for the KS test, don't say that the p is 0.200. Why? Because for the KS test, 0.200 is just the highest p that SPSS will report. It's not really the true p, it's just as high as SPS gives. Okay? So I would just say not significant or, big time. I wouldn't say big time. P is greater than 0.05. Now, I want to point out something which the textbook does explain this too, and something I've also further learned about. So I'm not going to make a big thing about it for the assignment, but I believe the more accurate way of looking at normality for a dependent t-test, a paired t-test, is you take the difference between the scores and you look at the normality of that. For example, I would compute a new variable. I'd say picture of spider minus picture of spider minus real spider. I'd get a new variable. I would now explore that new variable. So I'll show you in a second. This is best practice. I gotta get rid of. Do I want to save this? I think I better. Okay. That's what people ask me all the time, like, I forget what grad student it was, but recently someone, do you and your husband hold hands and talk about statistics? Well, yesterday we did on Valentine's. But I stayed at home, I worked at home, both kids were at school, and he's helping me with something I can't figure out. So we spent 4 hours together, holding hands and doing stats. Now, it wasn't all lovely. It's more like, why did you do it that way? Because that's how I was taught, and it's a good way. Well, that's a silly way. Well, you're silly. And or don't you understand? Can't you keep following? That's really how it is, but we have fun. It was fun. And that's important in finding a mate. I told that to my sister. You don't necessarily want a mate that you're going to stare in their eyes and think they're so beautiful. You need a mate that when you're 80 and you're staring in their eyes, you think they're beautiful. That's love.
That was really poetic.
Pardon me?
That was really poetic.
Thank you. I could do a Hallmark card.
Come from the notebook?
No, it came from my own being.
Did you not watch the notebook?
I did. And my sister.
It crushed me. I almost
I know.
died. And Dear John, forget about it.
I like the Notebook. It was my sister's favorite movie. So like after every little breakup she had, we'd have to watch the Notebook. My being sad movie has always been Anne of Green Gables. Okay? You know that something's wrong if Anne of Green Gables is on. That's what I looked for. I wanted a man that was going to say to me, it'll be 3 years before I finish medical school. And even then, there won't be diamond sunbursts or marble stars or halls. Gil, I don't want diamond sunbursts or marble halls. I just want you. No, the music came on. They're on the bridge. That was also my boyfriend test. If they could sit with me and watch Anne of Green Gables, keep her. Matt had a little tear. And he said he used to watch it with his mom. So, the end. He's perfect. Yeah, oh yeah. All right. Anyway, so we would I digress very much. Sometimes I sometimes hear though, people on course evaluations, they'll say, the thing you learned the most wasn't about the course, it was all my life lessons. But I don't know if that, okay, we're gonna call this, I'm just gonna call this difference, okay? Right now, oh, an incorrect name. What?
Because you're in variable.
No. What are you going on about? Do you see anything that's more than, I don't ever have had this. Okay, reset. I'm telling you to compute it. I don't know what's going on. This is very weird. Anyway, you would do that. I'm gonna move on. I'm not sure what's happening. I would get the score difference. I would then explore difference and look at if it was normally distributed. Okay? Now, why do people not really do this in real life? Well, usually it's the same. You'll find it's quite the same. The other is, imagine you guys have all those conditions and all those variables. You have to create maybe like a zillion different scores and calculate them and plot that. It's a pain in the bum. So we're not going to do that. The one thing, though, that you do have to do is normalize the mean. We want to look at an error bar chart next, okay? We want to be able to say, look at it to be able to see if there's overlap or not. We have to normalize the mean. And you guys can read more about that in the textbook if you want to learn about it. It's okay if you let this just go whoosh and follow the instructions, okay? It is when you have repeated measures, the mean is from the same people. So you have to normalize the mean because most of these statistics are assuming like independence. So you have to account for things. You have to compute something different. So we have to calculate an average then, an average anxiety basically for each participant. So what we're going to do now, as you can see, we first calculate the mean for each participant. So we're going to, hopefully this works because I don't know why it won't, but we're going to calculate a mean. Now, by the way, I can, in this function group, I can go in here and find mean. What is going on? Well, I'm going to just type it, okay? That's what I would do. I mostly type. Now I'm going to put picture, comma, real, bracket. Okay, so that's saying, it's just like in Excel, you know, where you'd say, except here it's a comma instead of colon. Sorry. Like, which one is this? Semicolon. And now you can go in here and figure this out. We could also do it arithmetically, but obviously, in my opinion, it's easier just to type it. It usually takes less time. So we're going to say, okay, what is going on? There's something seriously wrong. We're going to pretend this is just going to keep working. If something is wrong with the file, or I might have corrupt something. I'm not sure what's happening. Yours is working. See, it's just my SPSS. It's not what I'm doing incorrectly. So anyway, we would click on that. And here, what I'll just do now is I'm going to forget this. I'm just going to make this big. I'm just going to forget doing it in SPSS because it's not working. I've never had this error ever. So you guys can see this. Okay. Then notice I'm showing you at the top here. I could have done this in also I could have done this in syntax, okay? So then what you need to do is you want to get the mean of the mean. Okay? So we've calculated this mean value, which is looking at what is the mean of all of the person, regardless if they're in the spider or the picture condition. We now want to know what the mean is of the mean. So we would get that. And then we can plot that, which is called, so now we have, notice we've got picture of the spider, we have the real, and now we have this new variable called mean. We now want to know what the grand mean is. So the grand mean is, think of an Excel file. You have, if I highlighted all of the data like this and didn't care about which column or row it's in, and I get I could take the average of that, and that's called the grand mean. The grand mean is the average of all of your data, regardless of which condition the person is in. So it's just all of your data points. What's the average of all of your data points? So we calculated the mean for each participant across both conditions. And now we just need to get the grand mean. So to do that, we just have to run descriptives on our variables. So the grand mean then is going to be 43.5 because it is the mean of the mean. How can I should be able to do this, make this bigger and get rid of this stuff. There it is. Okay, so now we know our grand mean is 43. We now have to calculate what's called an adjustment factor. So the mean across participants is going to be different for everyone. So some people are going to have greater anxiety than others across the condition. So the fact that participants' mean anxiety scores differ represents that there was individual differences for different people. You know, I might be very scared of bugs. So my scores might be really high, regardless of if I saw the picture or the spider, okay? Or like my sister. My sister has a terrible anxiety of spiders. When we were in Costa Rica, I touched the tarantula and petted him reluctantly, but thought I should do that as a life bucket list thing. My sister couldn't even be in the room. She was gone.
Arachnophobia?
Yes. Which she doesn't have it so bad anymore because one of her co-op jobs, she was in biology, was being, she was a nature science educator for grade 6 students for co-op term. And she's telling them she's holding snakes and all these weird animals. And then there was like a spider on a swing and she started screaming. And then she realized like what she was doing to the kids, right? Here's this nature biology person who's screaming about like this little spider. So she stopped screaming, like she still was afraid, but she like suppressed her anxiety. And eventually, I don't think I can still scare her with the spider though. But, so the fact to eliminate this variability, which is unsystematic variation, because there's differences between people, we equalize the means across participants. So we adjust scores. So now we have to calculate this adjustment factor. Again, if you really want to understand this theoretically, read it over and over again in the textbook to understand. But this is not something that you have to, I'm not going to test you on this on the exam or anything, okay? So we make an adjustment factor. Adjustment is going to be 43.5, which is our grand mean, minus the mean, which is the average for each person regardless of condition. I could have also done that in syntax. And next, you have to create a difference between each participant. Mean score and the mean of all the participants, which is the grant. So we create another, we have to add our, what is our picture condition plus this adjustment factor. And then we have to do that for the picture condition plus this adjustment factor. The reason for all of this fiddling around is if we just plotted picture and real and just looked up the error bars of those, we would be losing the fact that this was repeated measures. It would be telling us an independent design error bars. All these calculations are because SPSS doesn't realize that this is repeated measures. We have to do math to make SPSS plot the correct error bars, okay? That's kind of the rationale here. You don't really, I want you to understand that. You don't have to understand like why you're doing all these little steps necessarily. But this is, and by the way, I bet you $100 that no one in the labs downstairs do this. They probably are plotting, I wonder, I don't know. They probably plot the like just those variables, but you shouldn't be doing that. If you're not doing these calculations, you're losing the fact that it's repeated measures. You're less likely to see differences because it's not accounting for the fact that there's very little unsystematic variance. So we do this again for real. And now we do a error bar. Again, just like we learned last week, remember for your scatter plot, you went to graphs and legacy dialogues as if you're going on a, seems like a cruise line to me, okay? And you're gonna click error bar. We want a simple error bar. And this is what we get. So that was a lot of pages. So this error bar, which note I say to the reader, normalize to the grand mean. That's telling the reader that I know what I'm doing. I understand my data is repeated measures.
Is that the point of the grand mean is to normalize our data?
Oh, when you guys know, okay, that's another topic. When you guys talk about normalizing data, they're using the wrong word. They're totally using the wrong word.
So like, when we
Okay, like, and I found out, I heard all this normalize, did you normalize the data? Normalize the data. This is what I heard for years. Jeanette asked me to help her with something about normalizing the data. I spent 2 friggin' days helping her to put it on the normal distribution, because that's what normalize means in statistics. Okay? She didn't mean that. It's called standardized. The whole bloody XFIS, the entire field uses the word incorrectly, and there's nothing you can do about it, I guess, because it's the way it's a jargon word, but it's incorrect word. It's really you're standardizing for that individual. You're taking one thing and dividing it by its standard error, and that's called standardizing. Normalizing means trying to fit it on the normal distribution. So, no, it's not what you're doing. What are you laughing at?
Just the pains of tech is just coming back. All this time we were wrong, so we've got to go back
That
to the
makes
course.
perfect
over.
sense to me. Because like normalizing, you're normalizing to like whatever variable you're.
The normal distribution.
Yeah.
Yeah.
So I'm bootstrapping, I'm applying log land of applications, I'm like, and then she's like, what's all this? You asked it to be normalized. No, it's not. And then she's like, I explained this to her, she's like, oh my God, we used the wrong word, you're right. So.
Yeah, normalize is in here too.
In my field, when I read the word normalize, it means normalizing to make it a normal distribution. Standardizing means you're taking apples and oranges and making them fruit. Okay? What you're doing for the Z-score, you're standardizing the Z-scores to compare them. It's a standard. You're taking the value, divide it by its standard error. We're not plotting it on the normal distribution. So I've learned what's the lesson there? Well, hope that when people start your field that someone actually knew the right word to begin with would have helped. But there's nothing they can do about it now. Number two, every field has different jargon words. And so you have to, like what I learned was when I work with, and we're very interdisciplinary here, I have to ask people, what do you mean by normalize? And then if I had just asked that, I wouldn't have had the problem.
Sounds like the word normalize is like published in every single.
Every single paper you guys read says
if we
normalize.
Standardize would it still be would it be accepted?
Well, what would happen is they would question, like I think I might have seen one person recently put I normalized, and they put in bracket, i.e. standardization of the values to tell.
So somebody.
So that the journal would accept it and people in that field would be able to read it, but that if someone like me outside the field wouldn't think that they were a moron.
Does Wayne know this?
I'm not sure that he does.
No, because it's like
Sorry.
something that I could beat him on later if he's like trying to be smart.
You might know what you're talking about.
I'm pretty sure that I've blabbed about this enough in this building that they know now. Because sometimes some people will say, we normalize. I mean standardized. So anyway, when we look at here, are there overlaps in these confidence intervals? Or is there any overlap? No. That means that for the means of each of these conditions are not from the same population. Therefore, they are different from each other. Therefore, without even doing a t-test, I can say that these are statistically different from each other. Okay? And so you might notice in some publications, I'm noticing this more and more, especially with pilot data, or like at a conference, they haven't done all their data yet, they might just show you this. And that's because they don't have a big enough sample to really do the statistics or whatever, they're not finished, but you can still see a lot of information. Again, why graphical representation of data is important. And you'll learn that. Well, you guys wouldn't have taken, if you have a chance, I don't know if he'll teach it again, when we basically try to rotate grad course. I'm like grad courses every so often for elective grad courses, especially for social science. So not this fall, but the fall before. Fuller did, of course, I don't know what it's called, but computerized applications or something. So it wasn't learning R, but he taught everyone how to graphically represent things, mapping. It was like heavily computer stuff, but how do you graphically represent data? I have made all my students, most of my grad students took the course, and my one student said that every student should take it. It was like amazing, and they learned a lot. And these are skills that you need. So if you hear about this, even if you don't have, like, I would highly recommend taking it. And that will give you more skills in a job. You can figure this out, but when you're working for government, they want to be able to graphically represent everything. And now the big thing is these, I find them dumb, but these like one-pagers of different statistics, but in graphics and stuff. And this is all the fancy thing now. But so you need to be able to do that. So take it if you can. So here, it's 95% confidence interval. We say there's no overlap, therefore the conditions are likely from different populations. They have unequal variance, and so our experiment did have an effect. But we don't know if that's statistically significant. I mean, I would bet $100 that there's no overlap, it's going to be, but we don't know at what level. So we have to calculate a dependent or paired samples t-test. Note here, big important, make sure that you're using the observed variables, not the ones you calculated for the error bar. Okay, we're using picture and real here, not our mean, not our adjust variable, not our picture 2 or real 2. You're not using the variables that you plotted for the error bar. It's the original. So in your assignment, you're going to have to report and interpret the t statistic. I want the t-test, like the actual value, your degrees of freedom. The degrees of freedom are important because it tells the reader what your sample size is and what power you have. P-value, and I want confidence interval. Note, for learning purposes, you're reporting both the p-value and confidence, although you wouldn't normally do that, but I think people are doing it now. And I also expect you to calculate the effect size. Effect sizes are like a type of correlation. How strong? Something can be, we could have a statistically significant difference between our spider and our real, but maybe it's not very strong. The effect size tells you how strong is that effect. So we go into analyze, compare means, paired samples. Oh, let's see if I should be able, well, I'm not going to switch back and forth. You put them both in. You then want to click on your options. Get some things. So this is what we end up with. So our N is the number of participants in each condition. Obviously, there would be, if one of these was 12 and one was 10, what would that tell me? There's big time error in the data. This is repeated measures. There should be the same people doing condition 1 as condition 2, right? So if I have a 10 on that end, that tells me like, ooh, like something's wrong in my data. I go back and figure out like, is there missing value for one person or what's going on? That's weird. You don't want to have that. Here I get the mean for each condition. We have our standard deviation and our standard error, so which is the sample standard deviation divided by the square root of the sample size. So back in the old days before SPSS, you had to calculate each of these things, but you could. I'm just gonna. So this is the standard error of the mean. This I'm doing high level, not high. This one. See if you can connect this to theory. Which of these conditions then has less error? Which is more likely to represent the mean if we look at our standard errors? Picture. Its standard error is smaller. Okay? So just looking at the standard errors, I can see, oh, well, there's more error. There's more unsystematic error in the real spider. Now, this is so small difference, we don't really care. But if I saw 2.6 on one and I saw 8.5 on the other, ding, ding, you gotta, like, something's wrong. Go back to your data. What happened? Did you code something wrong or whatever? Then you will also get a Pearson correlation. Obviously, in repeated measures, it's possible that the conditions are correlated because the same people do it. You would expect them to be correlated. In this case, it's highly correlated, but not statistically significant. And most likely due to sample size. I don't know if you're aware of this. The larger your sample, the more likely you're going to find a significant correlation. That's why you can have, there's like even funny correlation websites. They're joke, like for academic people, I guess, for jokes. I think they're funny. Like they'll find you have enough, you can take if you have 1,000 people in a data set, any of the variables you pick are going to be correlated, even if they don't make sense because of sample size. Then I go down again, and you'll see this is hard for me to show on here. So look at your table. So all the bold black stuff is obviously what you see. I'm explaining to you what these values mean. So the first column, you get -7. People sometimes freak out. It's negative. What is this? Well, it's just the difference between the mean scores. If I entered the variables as instead of picture and then real, if I put them real and then picture, that would be +7. So all it tells you is the order of which you put. All this is telling me is that real spider had higher anxiety than picture. Then the differences between the standard deviation. Then you have the standard error of the mean. So that's the differences between the participant's score in each condition. We then have you know what? I'm a moron earlier. I'm a moron. Pardon me. I was blabbing about confidence intervals earlier about crossing the 0 and how the signs had to be different. And I said it wrong. You want the signs to be the same. So here you can see, tells us the truth. 90, I shouldn't say moron. My children would say, don't use that word, mommy. So it's not inclusive. We're 95% confident that the true mean lies between -13 and negative. Notice that the interval does not contain the 0. I don't know why I said it that way. If your interval, if there is a difference, if there's not a difference, then it would include the 0. So if you see that your confidence intervals, you want them to have the same sign. If they're both negative, it's statistically significant. If they're both positive, it's statistically significant. If they cross 0, it's not. Okay, I apologize for messing that up. Is that clear? Okay, sorry. So it doesn't include a 0, so we can be confident that they're from 2 samples. Here's our t-test, which you can, we could do it by hand. Why is it a negative value? Well, again, it just has to do with the order. Picture had a smaller mean than real spider. If I had put them into SPSS in the opposite direction with real and then picture, the t-value would be a positive. Okay, so it like some people blab, like we found a negative t-value. Who cares that you found a negative t-value? Like that doesn't mean anything really. It's just which order. Then lastly, you'll see degrees of freedom here. We have 11. Why? Because the degrees of freedom for a dependent sample t-test is the number of people in your sample, which is 12. In this case, -1. So we have degrees of freedom of 11. Then we have a significance of 2 tails, which means I have no hypothesis. So the p-value is less than 0.05, so it's significant. So there's differences between the conditions. How do they find those out? Well, just so you understand, a 2-tailed test means you have no hypothesis. It means that you're not saying that one of your conditions should be bigger than the other. If you do a 1-tailed test, it means that you have a hypothesis that one thing will be bigger or less than the other. Okay? And notice that all you do is divide. You don't have to do fancy things. When you want a 1-tailed test, you just divide the p-value by 2. Okay? And I promise you, go look in your prof's papers. They have hypotheses all the time, and they report 2-tailed tests. Wrong. Okay? They're always doing that. They're always reporting 2, they're doing 2, or they're doing, they don't have a hypothesis, and then they report hypothesis tested. Like, it doesn't make sense.
So if you So I'm thinking of like papers on narrow that. Do they even show T-tests? Like, it seems like.
Most of the time when I see XFIZ is they're doing T-tests, but all they report is the P's.
So like, do they usually report T-tests and how they experiments? That's what I'm thinking of.
That's what you're supposed to do.
Because like, I see like the ANOVA.
Oh, but this is for simple. Like, most experiments are going to have more, remember, T-tests only do 2 means. Not that often that you have just 2 means, but in 4610, they just do a whole bunch of paired T-tests, right? So, most of the time you're doing an ANOVA, which is an F test.
So that's different again.
Different again. But hypothesis testing still applies. If you have a hypothesis, you should report a one-tailed p-value. And we'll go over this more another, okay? So how does SPSS come up with this? Well, we're doing a 2-tailed test. We want to be our alpha level, we want it to be 0.05. We have 11 degrees of freedom. The magic number then is 2.201. That means that if your t-value is greater than this critical value at this alpha level and these degrees of freedom, then it will be statistically significant. So that's how it finds this out. You could do this by hand. We got we got 2.473. Okay, so I wouldn't actually have to get the p-value. I can just calculate a t-test. I can look it up on the table. So this is how we used to do it in the olden days. Not my olden days. Dave, go look at his stats. Ask him to go see his stats books. Like ANOVAs and like pages and pages of ANOVAs he calculated by hand. Okay. Now he probably understands it better, in my opinion, but so if we had a hypothesis, we would divide our p-value by 2. We then have to calculate an effect size. Okay, for t-tests, you do an R. And in this case, you take your t-value and you square it. You divide that by also the square root of your t plus your degrees of freedom, and you square root all of that. Pardon me. Yes, you need to do this by hand. You just do it in Excel. It takes 2 seconds. Okay? And we get a 0.6. So, pardon me. Remember that for ours, a effect size of 0.1, 0.2 is small, 0.3 and 4 is large. So 0.5 and over is viewed as a large effect size. So this would be large. So I'm also looking not just that you've calculated the effect size, but that you're telling the reader if it's small, medium, or large. In this case, we'd say large. Then I write it up. I say a paired t-test was done. On average, participants reported greater anxiety when they held the spider compared to viewing the spider. Of course, I'm giving them means for each so that they can understand that. I have the wrong, sorry, I have a mistake there. That should be an 11, not 499. I don't have a good pointer. Right there?
Oh.
That should be 11, not 400. Yep.
In your previous assignment, when you report like mean and deviation standard error,
Yep.
you put a semicolon after the standard deviation. Was that just a typo?
No, I like putting you can put a semicolon or a comma.
Okay, so it doesn't matter.
I probably didn't notice that. I often use semicolons because you can see them better than the comma. The comma kind of looks like a period. Also, we are used to using periods for decimal place. But what did they use in Europe? And I don't know elsewhere in the world. You guys know? They use a comma. If you go to Quebec, even in French, you learn a comma. So they put 3,01. So I sometimes use a semicolon just in case someone doesn't understand, get them confused. But what you really do is you look to see what the journal does. Okay? If the journal though does terrible reporting, you can improve it and do it properly though. I know you're learning. Yes. You guys, you came into your master's thinking that research was this wonderful glass thing. And I told you in this class, I'm showing you that the wizard isn't real. Okay? Be a critical thinker when you read stuff.
You should really create your own journal.
The Journal of LA.
No, it gets accepted. Not good enough.
And then, so I'm saying the effect size was large. A 95% confidence interval was done, and I report that. Thus, the data provides evidence that holding a real spider produces more anxiety than a picture, which obviously is what we would assume. Okay, now I'm just going to show you the independent. This will be faster because you don't have to do any weird calculations with the error bar, okay? Now, I might not be able to even do this. Now, in this case, we have 24 people. 12 of them were in, so I have a group here. 0 is, I'd have to tell you, I don't even know. 0 is picture, 1 is real. Again, thank you, Angela, for providing wonderful coding in my variable view so that I would know what I had done, right? This is why you have to do this, so that you remember what you did. You open this up, you guys have a PhD, what if you guys are looking for data for this class, for the assignment? Dwayne hands you some data and they didn't code which was 0 and which was 1. You'd be like, I have 2 groups. I don't know which one's the experimental group at all, or whatever it is. So you'd fake it. So we have, again, so 12, we have independent people. Again, I'm going to look, I have to go back to this. Sorry, guys, I forgot. Oops. We've gone through most of this, so. As I say on here, we can't just plot an error bar. This is for dependent because it ignores the repeated measures. So we normalize that. Showing you again, a dependent test. If you want to understand it better, you're looking at systematic versus unsystematic variation, really. We calculated the test, and we do an effect size. As I have here, this explains then what type of effect size, and usually Cohen is reference for this. Cohen, 1963, I think it is. Have I actually read Cohen? Well, I actually did read a couple articles, but no. You know how you probably have learned you should never cite something that you didn't read. Okay. I totally agree with that, except when it comes to some of these stats things. Okay. Like I wouldn't cite Andy Field. I would cite Cohen. I would see that Andy Field cited Cohen, look up that reference and report it. I mean, it's like everyone has read, it's a common reference to give. So it's okay that you didn't read it, okay? When I was in your shoes, I didn't read quite a few of these kind of little things, like technical stuff. Like you guys are studying the manual for using the metabolic cart. Did you read the manual? No. Okay. So it's okay. And we do the effect size. So our independent now, though, is spider. We have spiders. We have group 1 looked at the real spider or held the spider. Group 2 looked at a picture. Now, one slight difference here is we have to care about homogeneity of variance. Okay, it's an assumption. We learned this on the very first day. You might not remember, but it's an assumption when you have 2 groups that the variance between those groups should be equal. If that is violated, then you're violating the assumptions of the t-test, and you should not be using it. Well, you actually can. You just look at a different line, okay? For repeated measures, there's another assumption. It's called sphericity. We're not going to learn that yet because sphericity actually only matters if you have 3 conditions. A t-test only can have 2. Okay, so we don't have to worry about it yet. So if we have 2 or more groups, we are assuming they come from the same population, therefore they must have the same variance. Here's a good graph. By the way, this isn't on your notes. I found this yesterday. This picture. I thought it explained things better, and then I didn't have to try to write my terrible designs on the board. So 2 variances should be equal. Look at these 2 distributions. Pretend that it's the spider and the real. Their standard errors, their variance are very different, aren't they? Look at the spread. This would be a very large standard error. This is a very small standard error. Okay, so we need to statistically test if these variances are the same. So that's an assumption. You have to check for homogeneity of variance. It's very easy. You use what is called Levene's test. Some people call it Levin, whatever. I used to say Levin. Now I hear people say Levine, so I tried to switch. But how would you guys say that? You say Levine?
How was Adam Levine?
I think it's L-E-V-I-N. No. Yeah.
I don't know. If it was an I, it'd be Levine. Yeah, I don't know.
He's an I.
Pardon me?
Adam Levine.
Maroon 5.
You know, the
From
judge
what?
on the- He's like the famous
He was
judge
the
on the
person
board.
who just, he's on The Voice and he just performed at the Super Bowl. This was the big.
I don't know anything about him. Anyway. Sorry.
He has a really
You
nice
definitely
voice.
know his songs.
Pardon me?
You definitely like know some of their songs.
If something is not played on CBC radio, I
Oh
do
my
not
gosh,
know
you're like
it.
my mother.
CBC radio 2 is what I listen to. It's not classical, like it's good stuff. But no, like if the word baby is in it or I'm not listening to it.
Yeah, he has simple lyrics like sugar, yes, please.
Exactly. Exactly. Now, CBC will play bad music sometimes if it's a Canadian, and then I'll hear it. And now they've got the CanCon. But like one right now, this Canadian guy, like, I'm so hung up on you, please don't hang up on me. I don't know. Oh, I dread if I hear it in the morning because I hear it all day long in my head. Anyway, I mostly listen to stuff that will probably be listened to 20 years from now still. Like it's not a fad. It's just called good music. So more.
What is that?
I don't know. I mean I also listened to Depeche Mode as a kid. High school. They weren't exactly like personal Jesus. You know, it's not exactly really great lyrics either. My sister loved Depeche Mode. Do you even know who Depeche Mode is? The beginning of, they were like one of the first bands that used electronic music. They were an alternative band from, it was the British. So it started late 80s, okay? And anyway, my sister was 3 years old when, because I was 13 when she was born. So we'd be in the car, and imagine a little 3-year-old kid, personal Jesus, and she'd sing. And when I got to go to I won tickets. My friend won tickets on the radio to see them at the Sky Dome in Toronto, and then we scalped those tickets for front row. And anyway, my sister really wanted to go with me, and the lead singer, his name was Dave. So I said, I'm sorry, Corey, you can't come. And she says, why? Doesn't Dave like kids? So we run a Levine's test, which is easy. By the way, it comes out. You get it when you run the independent t-test. Levine's test is exactly like the KS test. If it is significant, we conclude that the variances are significantly different and homogeneity of variance has been violated. If it's not significant, then we've got equal variances. Easy peasy. You don't freak out about Levine because SPSS gives you the correction to use, and you'll see that in just a second. So we explore the data. I'm going to skip some. You guys can look at some of this yourself. And the only difference is when you do explore with 2 groups, you're now putting your outcome variable in the dependent list, and you have to put your grouping variable or factor variable in the factor part, okay? So I'm then picking my normality with plots. Also, to get Levine's test, in the plots, I have to say I want untransformed Levine test. Okay, click that. And, or 11, whatever. You say, I could do different. You say normalize, I say standardize. Get it? From potato, potato. Levine, 11. Let's call the whole thing off. I'm sorry, Josh, I'm singing. And I have a bit of a cold too. I sing to my children every night. And the other night I went, Mommy, you need some water. Mommy, you kind of sound like a witch. That's what I got told. Because it's all cracking. Well, so we get our means, our standard error. Again, I'm going to do my standardized skewness and kurtosis score. Tell me something about that. And for the real spider, I go into legacies, I plot my variables. I didn't have to do all this adjusted stuff because it's independent and SPSS knows that. I then look here and I see picture and spider. They don't look perfectly normally distributed. Also, there's overlap. You can see that they're not separate from each other. So what does that say to us? It says that they might not be statistically significant. They might be from the same population. It might be that our experiment, our condition, our manipulation had no effect. But I do have normal distribution, which is important, so that's good. I'm just thought of something. Melissa's learning her stuff in R because Dan's making her, okay? And so she came to me with the last assignment, a bit worried because in R you can only get the Shapiro-Wilk and not the KS, okay? Or I mean, you don't know how to do it, that's all.
We're working on it.
Okay? Don't worry about it. You just need, either one of these is perfectly fine to report, okay? I just used the KS test because I was taught that. I was also, your book emphasizes the KS test, okay? Andy Field has the exact same book in R. In there, he only talks about the Shapiro. You're really supposed to look at both of them and hope that they say the same thing. In reality, what do researchers probably do? If they're not the same, they report the one that they like. Probably what really happens. Okay? I know. I should really have balloons in this class, but each time I tell you something, I like pop a balloon, popping your dreams of research and rigor. I mean, that's what I'm a methodologist. It's my job. I mean, I view it as that's my mission of life, is to make people be critical thinkers of research. Think about this stuff. So here we've got normal distribution-ish. I did box plots. There was no significant outliers. I talked about my normality. It was fine. I then have to talk about my Levine's test. So this is my statistic. By the way, Levine follows, so there's T distributions, there's Z distributions, there's chi-square distributions, and there's F distributions. Each test in statistics follows a different one of them. That just means that you look up a different table to find the critical value. You know, when you get a stats book, there's a reason why they put all those things at the back, because you're supposed to use them, right? So we get our degrees of freedom. So it's k minus 1. K is the number of groups. So we have 2 groups. So 2 minus 1 is 1. We have 22. The second is 22. That's because we have n minus k minus 1. We have 24 people minus 1 group. Minus 1 gives us 22. Now I look at this. Levine's test. Okay, it's not significant. If it is significant, then the variances are different and homogeneity of variance is violated. If it's not, we're good to go. You don't freak out though about it. So I tell my reader now, Levine's test for homogeneity of variance was performed. By the way, why do I have to say that's Levine's? Because there's other tests, okay? Just like you don't just say, a normality test was run. I have to tell my reader that I used the KS test, or have to tell them that I used Shapiro. There's like 50 zillion of them. SPSS, we have become lazy, and people just report what SPSS says, and they don't think about it, okay? For example, for many, many years, I wondered why Bonferroni was the only post hoc test people used in ANOVAs. Well, then I found out it's because it's just the default in SPSS. Okay. Now they've actually removed the defaults so that people actually have to think about it, which I think is better. So therefore, equal variance is assumed. Now I'd run my here's my error bar chart. Okay. And we've got 2 choices, simple or clustered. So we only have 1 independent group though. So clustered is when you've got a second group. So you can choose, so I'm doing, I want to click summaries of groups of cases. I then define it. Anxiety is my variable, my category or categorical variable, factor variable is group. And I get this error bar. There's overlap. Okay, there is a significant amount of overlap. So I would conclude that there's significant overlap in the error bars. Therefore, it kind of looks like there might not have been a difference in the groups at all. Not a significant group difference. So I say that. They're probably from the same population, they have same environment. Most likely, whether someone saw a picture or a group, it had no effect. Now we run the T-test, paired sample. What? I have the word pair there. I've never noticed. I'm only noticing my typos. That should be, it's not a pair, it's just independent. Again, you have to report all the same stuff and the effect size. Go to compare means. I now click on independent samples t-test. Anxiety is my test variable. By the way, when you're running t-tests, you can run them a whole bunch. If you have 55 outcome variables, you could put all 55 in that box and run them all at once. You don't go into SPSS and click one, run it, go into the other. I always laugh. I see people do that. I laugh. Anyway, be efficient. You can do it all at once. You then have to define your groups, though. Group. Notice it's question mark, so I have to define it. Group 1 is 1, and group 2 is 0. Please note that, here it is, see. If I had told, these are just labels that I have told SPSS. I defined group, the 1 as real and the 0 as picture, okay? I could have called the picture group a 6. And I could have said real is 9. Then I would put 6 and 9 there. It's whatever I defined my, like, it's not 0 and 1, it's arbitrary. It could be 342 and 907. Like, it's arbitrary. So, go in there, got my groups, get my statistic. So now I have the mean for each of my groups, my standard deviation, and I see my standard error. I want to report those. Now we look at our t-test. If you go to almost, where is this? I don't know what page it is. It's close to the end. Looks like this. Okay. You'll see here, there's 2 lines. Now the stuff in bold is what I've written. One says equal variances assumed. The other line says equal variances not assumed. Okay. So you don't freak out if Levine's test is significant, because if Levine's test is not significant, you report this t-test. If your variances are not equal, so Levine's test is significant, you report this one. And what it's doing, the t-value is the same, the p-value is the same, the degrees of freedom are weird. Notice 21.385. Okay? It is giving a more conservative degrees of freedom, so that you have to have a higher critical value in order for it to be significant. So you're being more conservative. You've got a problem, so you say, okay, the variances aren't equal, so I'm going to make sure that I'm even more confident in my t-test. Okay? I will know. I can tell right away. If someone will say to me, I read a paper, it says, I did Levine's test, and it wasn't significant. Variances were, equal variance was violated. Then they give me the t-test, and they put 22 for the degrees of freedom. They lied. They're cheated right there. I know right away then that they didn't do the adjustment on the equal variances because they've got a whole number for their degrees of freedom. You see? Like, it's telling me you didn't do the correction. So you just look at that line. And they find that the critical value, I'm explaining, you can look at all this up. It's the same thing for the, by the way, normally if it's, so this is not significant, there is not significant differences. We do the R. I'm asking you, even if it's not significant, that you report R anyway. You wouldn't normally do that. And you write it up. Another couple things I want to point out is this data is exactly the same, except one was set up as repeated measures and one was set up as 2 groups. We found significance in dependent, in paired, and repeated measures. we did not find significance in independent, but it's the same data. Why? Because the repeated measures design has less unsystematic error. When we have two groups, we have more systematic error. This is the beauty of repeated measures. You reduce your unsystematic error, therefore you increase your statistical power, and therefore you're more likely to find effects. As a geek, this is super cool to see, okay? And notice it's even a smaller effect. We get a lower effect size. How would I have done this experiment better for two groups? Well, I have two groups and I need at least 30 people in each group. I should have gotten more people if I have two groups. Okay, that's also why it is absolutely ridiculous in our building how we have two group designs with 12 people in them. It's not really statistically valid. You want to have at least 30 people in a group. So if you guys are comparing males and females in a repeated measures design, you should really have 30 males and 30 females in order for it to be valid. That does not happen.
Can you say that again, sir?
If you have two groups, like you're comparing males and females, you should have at least 30 people, 30 males and 30 females, even in a repeated measures design. Yep. Like in our field, a medical researcher would laugh at us because our sample sizes are so small.
I'm thinking about like phys that we have like male and female.
Yeah.
Or our trained and untrained.
Yep.
Groups.
And he couldn't get, no. But the other thing is you can, I'm just starting to close up because I see them up here. The other thing though is that it depends on what you're looking at. You guys are